All right, so let's continue the screencast of 8.2. So I decided just to stick with like your guys' class for screencast, because then it's like actually coherent. If the magnitude and angle of a vector v makes it the positive x-axis is known, okay, meaning guess what? I have a vector right here, and I know the angle. If the angle's at the x-axis, that's all it means. Okay. Then we can decompose the vector into its horizontal and vertical components, aka, oh hey, look, this vector. Let me know the x part and the y part. Instead of having one vector, I can say, okay, here's the x component, here's the y component, and then I can use it. So this is more or less what we've been doing. It's just like telling you in person right now, like, oh hey, guess what? If we solve for x, I have cosine x equals, x over the absolute value of v, so that's just the magnitude, the length of the vector. Surprise, your x component is just the length of the resultant vector times cosine. Same way, y is like the length of the hypotenuse times cosine, or times sine. I mean, we already did this. The main thing I want you to see is there's 3 ways to write vectors. You can write triangle brackets, right? A comma b, that's component form. A is your x component, b is your y component. But wait, I just told you your magnitude of the vector times cosine is literally x. That's your x component. The magnitude of your vector times sine is your y component. Okay, so once again, this is still component form. It's still x comma y. It's just written a little differently. And then we also can have it written in terms of a linear combination of I hat and j hat. Remember, I hat is along the x, j hat is along the y. What's along the z?
J hat.
K hat. You have a good bonus question. Okay. So, K hat's along the z. It's like I, J, K. The hat is like the little triangle thing. What's wrong? Okay, let's go over example 6. Alright, find the component form of vector v with magnitude 7 and angle 60. So I think this is going to help Abby's question. How do I know how to draw it? Okay, so how do I know how to draw it?
Well, the angle is 60. You use the
if the length is 7
Use a
of the vector.
Yeah, you use that thingy.
So I'm going to draw a set of axes.
That's what I meant.
Draw a set of axes. Okay, this is not the straightest, whatever. And I want, let's see, a length 7 at an angle 60 degrees. Where's 60 degrees? Which quadrant? First quadrant. I make a length 7, 60 degrees. There we go. This is 60 degrees. This is a length 7. What I'm trying to do is find the component form. Literally break it into the x and y parts. Break it into x and y parts. So how can I break this into my x and y parts?
Make a triangle.
I should have did it this
have
way.
the x and the y, like your vertical line and y.
Exactly. I have a horizontal and I have a vertical. So I have my x component. I have my y component. And we know from up above, we know x is equal to the absolute magnitude of my vector times cosine of theta.
How do you know the bottom line is that?
How do I know x? So up above, x is this, the absolute magnitude times cosine. If you don't remember, easy way to derive it. Easy way to derive it. Oops. Sokotoa.
So v is the magnitude?
You didn't do it yet.
What do you mean?
You haven't.
Yeah, I haven't plugged in
Yeah,
yet.
but how did you know that the line was that long?
Which line? The x component? Okay, so here, I see what you mean. Okay.
Wait, v is
Hold on. V is here, it was our vector. Notice it says vector v. Vector v. If it was vector a, I would go and put an a up in here. There we go. But it's not, it's v. Okay, to answer Gabby's question. How do I know how long the horizontal is?
Yeah.
Okay, so is this, I'm taking only the horizontal part of my vector. Is this like, does this match how long, how wide the blue vector is? No, this is way too long. So my horizontal part, I go from here to right there. So this is how long it's going to be. Literally this long. It just traces out the horizontal part. Oh my god, why does this not work sometimes? And then same way, if I wanted my y vector, I see I start here and I end here. So I'm only tracing like, it's almost like if I shone a light on it, like the shadow of it. So my other vector would literally only be this tall. Okay, yep.
Can't you just, like, don't you not need the x equals the after the y vector thing? Can't you just solve it and then write it in the, like, simplest, like the v equals AB? Like, can't you just get actual numbers?
I am getting the actual numbers. I'm not done yet. I'm answering questions as I go. So if I input here, I have 7 times cosine of 60 degrees.
Is that thingy always going to be the magnitude? Like VA?
So this, whatever letters here, yeah, that's the magnitude. Because when you have absolute value signs, it just gives you a magnitude. All right, did I answer your question?
Yeah.
So I went ahead and solved. I'm just showing all my work. Let's say you don't remember what it is for y. So I know y is the opposite side. So I could say sine of 60 degrees is equal to the absolute magnitude, is equal to the y component over the absolute magnitude. Here my vector is v, so that's what I put in. And then I find y is going to be absolute magnitude of my vector times sine of theta. So here y is equal to 7 times sine of 60 degrees. So that's going to be 6.06. So if I wanted to write this in component form, I would write triangle bracket 3.5 comma 6.06 triangle bracket, and then that's it. That's it. That's the whole problem. Questions so far? Okay. All right, example 7. Example 7, I feel like you'll like it even more. Example 7, so let's see. There's a couple things. One thing we need to be reminded. All right, so one thing I talked about, I think it's chapter 4, was tangent of theta is y over x. So here it's literally going to be, remember, your y, your x. So here it's going to be 9 over 2. So I have tangent of theta is equal to 9 over 2. Am I good to scroll up? Okay. It's equal to 9 over 2. How would I get the angle by itself? Tan inverse of 9 over 2, and make sure you're in degree mode. I mean, it's easiest because we want the angle. Keep in mind, so both of these x and y are positive, so that means we're in the first quadrant. So I'm looking at the angle. We want to make sure we talk about give an angle that's in the first quadrant. So when you plug this in, you'll get 77.5 degrees. Yep, that's it. That's that problem. Cool.
How do you know it's tan though?
Tangent is opposite over adjacent because I have my x component, I have my y component. I have my x component, I have my y component.
So how does that? Do we do a direction or anything, like north, west?
It just wants the direction of the angle. The direction is 77.5 degrees. If I don't have like that funky like bearing, if I just have the angle, then we're going to assume we're starting from the positive x-axis and like going around how we normally do.
Wait, what is the difference schedule? Like, when is this?
15 at 50. Yep, more or less. It's a little different. As soon as we finish this problem, I'll go look. Yeah. All right, example 8. A soccer player running forward. Who plays soccer?
Jonah.
Jonah, okay. Jonah is running forward at 7 meters per second. He kicks a soccer ball with a velocity 30 meters per second, angle of 10 degrees with the horizontal. What is the resultant speed and direction of the kick? Okay, so this one, this is a little more intense. All right, cool. Okay, so let's have this line be the ground. All right, so Jonah is running along at 7 meters per second. Okay, he's running forward, so that means positive. That's how I know he's going to the right. Because if we go to the left, it would be negative. Cool. And he kicks a ball 30 meters per second, angle of 10 degrees. So he kicks a ball at 30 meters per second at 10 degrees.
How is that arrow 30 meters per second? It's 10 degrees. You just go up 10 degrees.
Yep, I make it that long. So it's at positive 10 degrees. And I made 30, I don't know, maybe like 3 times as long as 10. So my pictures are not going to be 100% perfect to scale, but they're going to be close. That way I can figure out what the resulting vector is. Cool. Okay, so
Two-dimensional or three-dimensional?
we're only doing 2. I'm not doing 3 dimensions with you guys. Yep. Okay, so the first thing I'm going to do is find the first vector in component form. So I should probably label these. Okay. First thing I'm going to do is find v1. Find v1 in component form. So here, my soccer player, Jonah, is going to be player 1. So what is my first vector? How do I write that in component form?
7, 30.
He's running, right? Since he's only running forward.
That doesn't make sense.
Is he flying up in the air? Nope. He's only running forward. That's it. He's running forward. He's not Harry Potter. He can't just go and fly. Sorry, you're not a wizard. Okay. Okay, so the next thing we want to do you have a guess? What do you think I'm about to write?
Find V2.
Exactly. Find V2 in component form. So that's the soccer ball. Okay, so, how could I figure this out? So I know I could write this as absolute value of the magnitude of the vector, cosine theta, comma, absolute value of the magnitude times sine theta. That was one of the 3 things I gave you. Okay, so if I plug in values for this, I have 30 times cosine 10 degrees, 30 times sine 10 degrees. I find that the soccer ball's vector will be 29.5 meters per second forward in the x direction, 5.27 meters per second in the y direction. Okay, cool. So far, so good. We've broken both these down into vectors. Yes, Jonah?
Do you only use those little equations when it's
We have an angle. Yeah. I could use it for, you running. Because what's sine of 0 degrees? 0. So, and then what's cosine of 0? 1. Yeah. So I could have. Yeah. So these all are equivalent. So I have, let's see, the important ones is this one and this one. Because now what I'm going to do is vector addition. My resultant vector is literally going to be vector 1 plus vector 2. So we're going to be adding vectors. So we're putting everything together. So this is a way we could have solved the other problem. Instead of drawing it out, doing these triangles, go straight to this, break it into the components, and then add them. All right, so I'm writing every single step. That way when you come back in the notes, or you watch the screencast, you're like, got it. I see how you got it.
I have a question.
So vector 1, yes.
What's the point of adding the vectors? Why?
That way we can find the resultant. Instead of having to go through and
the
like,
resultant is adding the two?
yep, I add the two vectors, I can find the result, I can find what the ball is actually going to be moving forward at. 5.2. It's not 5.27, I'm sorry, it's just 5.2.
It's not 0.7?
No. That moment when you can't even read your own handwriting and you think a triangle bracket's a 7. Awkward. Okay. Awkward. Let's keep going. Okay. Okay. All right. So you add like the corresponding parts. I don't know another way to say it. Like the corresponding. You add your x's together. So that's 7 plus 29.5, and you add your y's together. Your y's are 0 and 5.2. Okay. So I find my resulting vector is going to be 36.5, comma, 5.2. Okay, so are we done? Because what we're trying to find is the resultant speed and direction of the kick. I have the x and y component of the resultant, not the actual length. Okay, so now let's find the magnitude.
You have to find the hypotenuse? Is that what it is?
Yeah, so to find the speed, aka the magnitude, it's like the absolute magnitude of r. I'm going to say, okay, well, absolute magnitude is going to be square root of 36.5 squared plus 5.2 squared, all square root. It's basically equivalent to 36.9 meters per second. Because remember, these are all meters per second. It's a speed. And then this fifth and last step, nice and short.
What is that?
Can you see a little better? 36.9 meters per second. All right, and then the fifth step. What's wrong? Because we have the speed, now we just have to find the direction. All right, and so to do that, I know tangent of theta is literally y over x. So here that's going to be 5.2 over 36.5. So our angle is just going to be tan inverse of 5.2 over 36.5, also known as 8.1 degrees. So, ready for the final answer? 36.9 meters per second at 8.1 degrees.
Will we get points on if we don't write like northwest?
It's not northwest, it's literally just 8.1
like
degrees.
For example, because I don't know how to do that.
The bearing? I more care about like this. This is a great problem.
It's gonna compass over.
Because
Okay.
if like